Good day. My name is Jannick Schmidt. I'm the CEO of 20 LCA Consultants. I will now give a presentation of our current project on 500 food LCA database. Good. The 500 food LCA project. The project is funded by selling funds which are part of the selling group in Denmark. They own the largest retail chain in Denmark. The project itself is carried out by us, 20 LCA Consultants, and the green think tank in Denmark, Concito. The timeline of the project is that we will provide data sets in the beginning of November this year. The reporting is provided by December this year. And the final transparent database is also provided before the end of the year. The project, what is the scope of the project? It contains 670 products in total, and behind that is 4,200 data sets in the foreground of the database. It also links to a background database with more than 10,000 data sets. The database is global, so it's fully founded in a global database, which includes 43 countries and 5 rest of world regions. I'll come back to the geographical scope of the database later on. To elaborate a bit of the different products, the 670 products, that is composed by 500 food products at supermarket, around 160 crops at farm, and 8 to 10 animal products at farm. Who are then doing all this stuff? Well, currently we are a team of 5 people at 20 LCA working on the database. Ivan, he is taking care of the data collection, production data for food processing. Stefano, he's doing the modeling of agriculture and programming the database. Michele, he takes part of data collection for fertilizers, fisheries, and database management. Miguel, he's programming metadata and managing documentation for more than 4,000 data sets. And myself, I'm the team leader of the project, and I'm responsible for methods and modeling, as well as the reporting of the whole project. The methods. Well, first of all, we are using the standard for life cycle assessment, so everything is following the ISO standards on LCA. When it comes to the modeling of byproducts, that's consistently modeled using substitution in accordance with the ISO standards. So one example here is that when we have a rapeseed oil mill, and I would like some rapeseed oil here, it comes together with the byproduct of rapeseed meal, which is used as an animal feed. And here we include the substitution of alternatively produced protein and energy feed. When it comes to the market mix, we only include flexible suppliers. One good example here is that, here again, that's me. I would like some fish, in this case here, cod fish from fisheries in the sea. The problem about codfish is that the stock of cod is constrained. We are simply fishing to the very limit. So if I ask for one more codfish, there will not be caught one single more codfish, simply because we cannot take more fish out of the sea. Therefore, I will affect an alternative supply of fish. And one example here could be carps, or in this case here, tilapia, which is fish from aquaculture, which is basically accounting for all of the increase in fishery production. Okay, the LCA of the agricultural part is obviously an important part of a food LCA database. So how do we do that? Well, we are combining a long range of different data sources. The main data source is the FAO stat. database where we simply make a bulk download for all information of all crops and animals. That's production volumes and harvested area. We also make bulk downloads of available fertilizer data per country in the world from the International Fertilizer Association. We combine that with fertilizer recommendations and land use data from the FAO-stat, and thereby we can allocate the total fertilizers on every individual crop in every country in the world. We also take account for all the nitrogen, phosphorus that comes from animal excretion, which is also based on FAO-stat data combined with standard coefficient data from, in this case, IPCC. We have crop property data on protein, dry matter, etc. We also have soil data and emission factors and other coefficient data on crops and animals. And by that, we can create very detailed emission inventories for every crop in every country in the world. Everything that is not covered by the above mentioned data sources is completed using data from the Exio-based database. I come back to that. When we do all this, we are creating transparent emission inventories as well as nitrogen balances for every type of crop and every type of animal. Here we have a very short snapshot of an example of an inventory. If we take the column over here for wheat in Denmark, what we have in the top is the yield of wheat in Denmark. You can see the data collection unit is 1 hectare in 2016. We have some crop properties, dry matter, protein content, phosphorus content. We have input of nitrogen, phosphorus, and potassium fertilizers. We also have crop residues here. We have the total harvested area, so all the data you see here can easily be scaled to actual production volumes. And then further down here, we have the emissions of nitrous oxide, methane, NOx, ammonia, etc. We do exactly the same exercise for all different animal production systems. We also do that in all countries and regions in the world. Here in the first column, we see a Brazilian beef cattle. We have an output of live animal. It should be mentioned that numbers you see here are all in dry matter. That's done to be able to make a mass balance. We also have nitrogen balance, but that's not shown here. It's actually funny to see that even though we have a dry matter mass balance, we have water in the mass balance. That's to account for respiratory emissions. So we have the output of products and emissions and manure and inputs of feed and oxygen, and we can see we have a complete mass balance in dry matter here. When we do the life cycle inventories of the food processing industries, the food industries, we are collecting, the main task here is to collect data on ingredients. Of course, also losses in the production processes. Here's an example of a salami pizza. We have the data source specified. We have some standardized data extract from databases we have got available on ingredients. We have specified whether it's cooled or not. And we have a reference flow. And we have a dry matter content, and then we have all the ingredients. For each of the ingredients, we also have the dry matter content, so we can make a dry matter mass balance for every of the 500 inventoried processed food. We have energy consumption and water consumption and byproducts. Good. All these data, they are then linked to a background database. That's where we get our electricity, our buildings, a large part of background transport, as well as machinery, etc. The background database we're using is the Exio-based database. Exaiobase is a hybrid input-output database, which is available for free on the webpage you see here at the top. It has a granularity of 200 products and 164 activities or industries. The geography of Exaiobase is 43 countries plus 5 rest of world regions. You can see that in the picture here, where the green countries here, that's individual countries in Exaiobase, and the others are the groups of rest of world regions. The current version of Exaiobase has a base year at 2011. We are currently updating that to 2016, and you can read more about this update project on the web page indicated here. We also take into account indirect land use changes. You cannot make a database for food products without accounting for that. Land use changes account in total for 11% of global greenhouse gas emissions. So eliminating that would approximately reduce the impact of food by 50%. So that would not work. The Exaiobase database has a lot of extensions, which are more or less similar to normal LCA databases. There's a lot of waste fractions, which is of course relevant for how we treat food waste and also end of life of all packaging materials. There's 62 emissions, 37 resource categories, and of course also land use. I mentioned it was a hybrid LCA database, which means that the reference unit of reference flows in the database are in euro, in kilograms, and energy units. Okay. Wrapping up here, mentioning the deliverables and the conclusions. First of all, the characteristics of this database we are developing. It's fully flexible. The database is parameterized, meaning that we can change any parameter, that being a emission factor in the IPCC, it could be fertilizer recommendation, or we could update the entire Faustat bulk download to another year, and we could recalculate the entire database. We could also swap between modeling assumptions so that we could change from could be average market mixes instead of substitution, or the flexible producers, or we could introduce allocation instead of substitution. So we really have a model that is open for manipulation and future development. The deliverables of the project is a standardized data sets with results for these 500 food data sets here in the first case. I'll show an example of what that will look like on the next slide. Of course, there will be reporting describing methods, and finally, we'll provide the entire database for our LCA software. So, of course, we will not stop here and link back, because currently we have 500 food products, and they are currently placed mainly in DK, because the commissioner of the study is the largest DK retail company. So therefore, we have placed it in the Danish corner of this global model. So of course, it does not take much work to take these 500 products and then place them in, it could be in the Dutch supermarkets or in the Indonesian supermarkets, and we would automatically link to the markets in these different countries, taking into account their agricultural and other production systems. Of course, it's also relevant to expand the scope of the database so that we have more than 500 food products in the supermarkets. With that, I would like to just briefly show this example of a data set with results. Here you see the results as kilogram CO2 equivalents per kilogram of product. In this case here, it's a pizza salami. There's also some additional data on the energy, fat, carbohydrates, and protein in the bottom. So this data can be extracted as well. The database is linked with a very detailed database of properties of different food products. Every product in the database has a unique ID. Of course, it's also linked with international classification systems. But here we have a unique ID that can link to the underlying data set, so we can easily you can easily dig down and see what are the assumptions, data sources, and ingredients in every bottled product. With that, I would like to say thank you for your attention, and I'm looking forward to seeing your comments and questions.